So before we start the next lecture series, I wanted to touch base on this idea of air infiltration and measuring it. We accomplished that in the last lab where we included it in, and I didn't give you an adequate enough discussion about that. And I meant to move that over. I haven't done it yet, so I want to quickly cover that with you. So here we have some measuring devices. The first two images are wall barriers, or excuse me, door barriers that have been set up that allow it to have a fan input in it. And that fan runs to create a pressure differential between the outside of the building and the inside of the building. And by putting that pressure differential in, it allows air to be sucked in through the crevices and openings in the building envelope. And that's a way of measuring how much air invades the space at any given hour. They can measure the pressure differential on both sides and then make a determination about how leaky a building is. And there are standards that we can use to just assume levels of construction, and that's what we did in our lab. But we can actually physically measure it, and it's a way of creating like the performance criteria of any given building. And this last image over on this side is, I thought was pretty good because it's an idea of that the efforts that good construction methods will entail in order to create that kind of an air barrier system to reduce air leakage. So here we have this blue air barrier tape being applied. It looks like it's applied to anywhere where it looks like there may be breaks in the system, whether it be the application of fasteners, or in this case, they're putting a panel box on, and it looks like they're trying to be very careful about sealing around the passages of those. So today, this idea of controlling unintended air entry into the building, air infiltration, is really important, and I wanted to just cover that a little more with you. So now I wanted to move into this idea of the two things we're going to discuss in this module are glass, and then we'll move into the heating and ventilation. And the glass is really just a continuation of our last discussions about building envelopes. And I wanted to just touch on a few things that you'll be facing as architects in the future. You're always going to be faced with this idea of making choices, and we went through that with the window of deciding whether to buy a better window or not. And I've hyperlinked a couple of pages here in the slides if you go ahead and download the link. And they go into some discussions about, the values, the value added of adding double panes or triple panes and whether they're worth it or not. And you've already done some evaluation and come to some conclusions on your own. So these would be a great reference to take a little read through. And maybe just even, I didn't spend enough time discussing this idea of the value or the insulating value of air. So I've shown you this graphic before to give you this idea that each layer creates a certain amount of insulation value. So we have an exterior temperature, an interior temperature, and as it passes through each resistive element, the temperature decreases. And I discussed that the idea of at some point there's a condensation layer that forms. But beyond that, this idea that air is an insulator is very important. And I think it would become a question for me, why are 3 panes of glass better than 2 panes of glass? Or why not just 2 thicker panes of glass and eliminate the one in the middle? And the reason for that is that the air can only insulate up to about a half to 3/4 of an inch before the air starts to circulate and convect. So as the air cools on this side, it is driven down. As it warms, it rises on this side, and we get this convective transfer of heat. And that effectively limits the amount of airspace that is effective for insulation between glazing panels. And so in order to increase that, the addition of the extra piece of glass is not because of its insulating properties specifically, but it's by its ability to divide off these 2 air layers between each. So there's a lot going on in this idea of single pane and double pane glass, and I kind of wanted to bring that up as a topic of discussion. Further expanding on this, and really Glass is going to be a big part of architectural practice for you. There's going to be a lot of discussions about coating systems and other things that I hope to just touch on briefly here in the next couple of minutes. But there's this idea of low emissivity coatings. And we talked about this concept of emissivity. It has to do with radiant energy. And there's many coating systems that are available. I believe this is hyperlinked out to a resource that goes through the idea of the value of these coatings. And their intention is to block this idea of radiant transfer through the windows. In most cases, depending on which surface is coated, it's intended to usually block out solar sunlight radiation from entering the building and adding additional heat. But it also can be very effective in cold climates coated on the right surface to prevent radiant heat losses from the inside of the building. And that's relatively difficult to understand to a novice because you don't think about heat as having a radiant property to it. But if you were to look at that from in a thermal imaging camera, you would see that rooms look very red to the outside, which would look very blue. And so that heat energy easily can get transferred through the windows. So these e-coatings really improve the thermal performance of window systems, and they're relatively difficult to understand. So a brief review of these coating systems, they discuss where the coatings are applied to the glass and how they improve the insulation value is well worth your time and education going forward. And as I said, these coating systems, they get very complicated. So in this case, we're looking at glass. Excuse me, let me back up here. I want to get back to full screen here. So here we have this idea of the number 1 surface of glass, the number 2 surface of glass, the number 3, the number 4, and each one of those in commercial glazing systems can have different coatings to them, whether it be tinting, emissivity coatings, fritting, which is another technique, and I'll discuss that in a minute. And all of these can affect the appearance of the glass and the thermal performance of it. In many cases, the appearance of the glass is really critical because it's one of the few controls that architects have when we start using large expanses of glass to differentiate our panels from the next building next to it. And so the color rendition, the way it reflects, how much it reflects, are all important issues. And where we choose to put coating systems on this glass radically affects the appearance of the glass. Here's a really nice graphic for this idea of all these coatings on our surfaces. We talk about, once again, this reminder that these low E coatings reflect radiant heat, and it can be applied for warm and cold climates depending on what kind of performance we want. And windows come with rating systems, and its idea of solar heat gain, which I'm introducing here. The solar heat gain fraction is how much light is allowed to enter the building, and that goes to its energy performance. So we track all of these kind of values when we rate them. So this Energy Star certification you'll see attached to many of the glazing systems, especially at the residential level. And it describes, and this is very interesting, it describes, for instance, what climate it's recommended for. So here we have it certified as an Energy Star performing glazing system in this climate. This is because it's probably a predominantly cooling climate, and it's not certified for here because this window is not designed to be performing in a warm weather climate, and because we would have opposite performance criteria for it. And then we get the U factor. Once again, that's a reciprocal of the R value of it, and that's how we measure glazing systems. We have our solar heat gain coefficient because this has a low E coating on it. It's also double glazed, and there's another term that's introduced here, and that's argon. Argon is the gas that fills up that space between the glass. So between these panes, many times in high performance glazing systems, we don't fill it with regular room air, but we use argon. Argon is an inert gas. It doesn't react well, and it has a poor thermal conductivity, so it actually improves the performance over regular room air as far as insulating properties. So a lot of valuable information here. I don't expect you to absorb all of this in Environmental Controls 1 because this is going to be a big part of architectural practice for you in your profession going forward. Plenty of resources for this. But there are visual effects that you can add to glass that are important to know. They can affect both the way the glass looks, and this one of these I wanted to bring your attention is this idea of fritting glass. It's the application typically of a ceramic coating to the inside, or it can be to actually any surface of the glass. And its effect is to create both a visual aesthetic. So here we have a fritted glass, but it also reduces solar heat gain because it reflects light and reduces the amount of transmission through the glass, just like any kind of shading system would. This is a hyperlink to a window calculating software, and we're going to be using this. This is the residential version, and there's a commercial version of that. I'm just making you aware of that. We can do a lot of analysis with these outside pieces of software, and that'll be part of our lab work. And next we'll pick up on heating, ventilation, and cooling. So that concludes the glass portion.